Okay, welcome guys. Today we are going to do the first lecture of our interesting class, Culture of Science and Computation. In this class, we are going to examine the historical developments in the computation and problems that are solvable by computers, such as economics problems, scientific problems, astronomical problems, biological problems, structural engineering, civil engineering problems, accounting, banking, finance. So the purpose of the course is to introduce you the use of computing in various areas of the life, and what are we going to do with our computation, and we will try to understand the perspective of the computing as a whole from the top. That's what we are going to do through the semester, and sometimes we will be inviting invited lecturers, maybe a few times, from the industry, so that you can get some understanding about what they are doing in real life. Feel free to write the chat box so that I can reply or comment, or you can only write comment as well, so I don't have to reply to some. So there are some issues, and you have some future courses that you are going to take. The idea is to plan your future correctly so that you will be successful. And in order to do that, most people believe it is very nice to understand the past and the mistakes done in the past, so that we don't make those mistakes second time, or we extract information from the past knowledge. That's how we build up information. So either positive or negative information helps you to organize your future. It is sometimes difficult. I will start this lecture by giving examples from the history with the false projections made by famous people. One of them is, since the planning is difficult, I think there is a world market for at most 5 computers. That sentence is said by chairman of IBM, Thomas Watson, in 1943. He said at most 5 computers can be sufficient for the world market. Obviously, he was wrong later. Second one, in 1949, computers in the future may weigh no more than 1.5 tons. So they say there will be lightweight computers, and so maximum 1.5 tons. So it is very interesting as well. This is a very interesting false comment. The chairman editor of Prentice Hall in 1957 said, I have traveled the length and breadth of this country, meaning the United States, and talked with the best people. I can assure you that the data processing is a fad that won't last out for a year. So he says it's a fashion for that year, and that fashion, named as data processing fashion, will die away in a year. So no more than a year, people will forget data processing. That's what he said as an editor of the book company. He didn't want to accept books in data processing for publishing. That was an excuse. Digital Equipment Corporation, which is very famous, which has been very famous in mainframes and mini computers. Mini means a little bit smaller than mainframes, but bigger than personal computers. He said there is no reason for anyone would want a computer at their home, so no need for home computers, they said. It was after 1 year after first Apple computer was built, said in 1977. That was one of the computers, DEC Wax, that was mini mainframe built by Digital on the right side. And famous Bill Gates, when he was young in 1981, when MS-DOS was first came out, he said 64K ought to be enough for anybody in one lecture, in one talk, company talk. Obviously, he was wrong. But over the years, we suffered a lot from the Intel 64K architecture barrier. Lately, it is no more an issue. More interesting knowledge, Beatles were rejected by the recording company, which is very famous, Decca, a recording company. They said they don't like their music, and guitar music is on the way out. So they said guitar is quickly dying out fashion, and guitar music has no future. That's what they said in '62. So they don't accept it, and that was Beatles. So the motivation is history of computers. Let's talk about history of computers so that it can help you to understand where we are now. Keep in mind that this history of computer thing is only for this lecture, the first week. In the coming weeks, we will not be going through history of computing, but we will be discussing different subjects of computation. Obviously, they may include historical information as well, but that won't be similar to history of science or history of computation. That will be different. So, famous computer, Abacus, the early days, let's call it, about first days. On the left, we are seeing two different Abacus versions. One of them is Chinese, one of them is Japanese. At the top area of each abacus is used for fives, one hand or two hand. So it's basically started from the hands. Bottom area is used for one. So it is started from the hand analogy. It's 1, 2, 3, 4, 1, one hand, and it is on the other side. Another on the other side. So upper side is for hands, lower side is for fingers. So that's how they made analogy with the hand calculation to the device. And it is like having how many? It is like having like 10 or so people using fingers together. And yeah, that's from the book, and it says 1998 written in the abacus as the digits. Abacus is still used in some areas today because people are used to it. In Japan, schools have abacus contests, abacus use contests for gaming or for festival thing. You have tons of calculations to be done by the abacus, and children are using abacus to solve it. It is very fast, and it also helps you to visualize the quantities much better. So it's much better for your brain. And in Japanese abacus festivals, what I have seen is they use abacus without the abacus. So they use their fingers, they memorize all the table. They simulate the abacus function, the children, in their head without abacus presence. So that's also possible. In some societies, it's still basic computation. There are videos on the YouTube where you can see abacus is being used on the market by the people. Second interesting device is slide rule. Slide rule was very famous until I was a student. In 1980s, people have been using it. In 1970s, it was being used. And it is used for multiplication, division, roots, algorithms, and trigonometry. It is based on the original work of the Napier, and the basic principle of this slide rule is logarithm turns multiplication into addition, division into subtraction. Subtraction is mapped to sliding on the number axis. So if you can subtract and add multiple things together on top of each other, you can do multiplication and division, and using Taylor expansion, again with the tables, with the table with the linearization, not the Taylor expansion, you can find logarithms and trigonometrical functions using the slide rule. You can compute actually. The original idea is to convert higher degree functions using logarithm to addition, additive operations. It was an engineering tool for years, for tens of years in the world. All kinds of engineering and accounting areas were using this as a calculator. Actually, some people preferred it over the calculator, over the electronic calculator, because they said it is more reliable. They see what they are doing as they are doing. This is one advertisement. Having a computer by IBM. Having a computer means 150 extra engineers. So by the engineer, the advertisement contains slider. So each engineer is symbolized with the slide rule because the computation was done with the slide rule. after 1970s, electronic scientific calculator that can take sine, cosine, logarithm, etc., made this obsolete. Yeah. That the original calculator, when we go back 1623, Jacquard calculator. Jacquard made a calculator like the one in the picture. It was able to make simple calculations using mechanical interaction. Until after 3 centuries. Then it is rediscovered in 1957. So it was an original idea, but has no impact in development of the recent calculators. It's an historical information. Pascal has famous Pascaline device shown below. The famous Pascal. He worked in the device for 3 years between 1642 and 1645, 3 years. And the device is a mechanical calculator. It looks like it is similar to 20th century mechanical calculators. It can add and subtract by rotation of the knobs. So it is possible to make addition and subtraction. This is the close-up. This is the close-up of the machine, and these are the displays. And this is input, and these are outputs. So you can make addition and subtraction using this machine. Basically, the slide rule is mechanized. So mechanical slide rule. Same principle apply with the mechanics as well. With the slide rule, you do it manually and you look at it in detail. Leibniz, German philosopher and mathematician, as he was working on addition and multiplication using Pascal's calculator, he was the first one to describe the pinwheel calculator in 1685. So that's before French Revolution, and invented the Leibniz wheel used in the arithmometer. I don't know what it is. The first mass-produced mechanical calculator. So add, subtract, add in this way, subtract in this way, change digit, add, subtract, change digit, add, subtract. Leibniz was also famous for the improvement in the binary number system, which is the foundation of all digital computation today. So it's before French Revolution, German. This is interesting. Jacquard, 1752, 1834. So it is during the revolution. It played an important role in the development of the earliest programmable Loom. Loom means dokuma tezgahı. Loom, which in turn played an important role in the development of other programmable machines, such as computers. So I have a video of this. It had used punch cards to control the development of the fabric. Later, Charles Babbage had one of these pictures of this loom, and Charles Babbage, who invented Analytical Engine, Charles Babbage had some influence from this Jose Maria Charles Jacquard Loom device. And I have the image for that. I have the video for that. Hope it works. If you don't hear sound, let me know. If you hear sound, sound is okay. Please write sound is okay. Can you hear sound?
Yes.
Okay.
This is a mechanical Jacquard loom. This technology was developed in France in 1803 by a weaver named Joseph Marie Jacquard. The key thing about this loom is that it controls every warp thread, the threads that go from the front to the back of the loom, individually. Because it can do that, the loom can create very complex, fancy patterns in the cloth more quickly and with greater accuracy than the technology available before this loom was developed. These cards are what carry the instructions that are read by the apparatus on the second floor that tells the loom what pattern to create. The holes in the cards are read by a series of pins up in the apparatus, and those holes tell the apparatus which threads down here should be raised for each pass of my shuttle across the warp. Some of you might recognize these cards as looking similar to computer punch cards. Back in the early days of computer technology, punch cards carried instructions that told the early computers what kind of calculations to do. So this loom is the great-great-great-grandfather of the computer technology that we all use today. And that technology started with a machine that produces cloth.
So, as you see from here, there are punch cards that control the fabric pattern. It controls the looms, and so that you don't have to memorize how to make the pattern. It is automatically done by anybody. It can be operated by anybody who can push and pull the device. Later, this kind of approach enabled automated powered machines that produce those fabrics with the patterns on it.
Of pins up in the apparatus.
Okay. So, a French inventor, an entrepreneur best known for designing, patenting, and manufacturing first commercially successful mechanical calculator. That's what I have said before. Arithmometer. Arithmometer was manufactured from 1851 to 1915. And during that time, there were about 5,000 machines. 75 years. It is 75 years. There were about 5,000 machines built during that time. So it is arithmometer. Eventually, about 20 European companies built clones of the arithmometer until the beginning of World War II. So arithmometer is very famous device invented by French invented Charles Xavier, Thomas de Colmar, arithmometer. Babbage, who had the idea of Jacquard Loom, thought about something programmable, something that executes, not programmable, but executes a predefined program, some device that can execute a program, and the programs are those cards. Cards are programs, so it can process those cards. Invented difference engine and analytical engine. Difference engine and analytical engine. And that was the actually first proper analytical engine, actually. First proper model of the computer. Analytical engine is later implemented because it was too hard to implement. Later implemented. Difference engine was also making some computation, and I have the video for you. And difference engine, Babbage couldn't finish it in his lifetime. His son finished it. Probably they were rich or had enough money for building those kind of things, or some having some grant from the rich. So they were able to make the difference engine after his death. And the analytical engine was also done later. And analytical engine can be simulated in animations. I have seen certain videos who is done as graduation projects. So people can make can simulate analytical engine as animation projects. So it is basically a mechanical fixed code microprocessor. Anything you see in microprocessors actually can be implemented mechanically. The problem is it will be expensive, it will require energy, and it will create errors, it will stick, etc. So you need to have oil in certain places. So it has to be very precise and expensive. In the early days, they did it. There were computational devices like that, but later everything is electronic. This is the difference engine. Difference engine was never fully built. Babbage drew up on blueprints, drawings for it while still an undergrad in Cambridge University in England. But while it was in process of being manufactured, he got better idea and left the work of difference engine, and he moved to the analytical engine. Analytical engine later built completely by George and Edward Schutz, based on the Charles Babbage design. And there was a film footage also existing about the machine made by George and Edward Schutz. There are also later machines built by other enthusiasts to replicate the famous machine. Let's see how it looked like.
Charles Babbage was the only child of a tyrannical London banker, a bully at home. But his money kept his son and heir financially comfortable for life.
Yeah.
Cambridge educated in mathematics and supremely self-possessed, Charles became an iconoclastic writer and habitual inventor. In 1832, the drawing room of his London home became a showcase for demonstrations of a small section of his difference engine. a far from finished device by which he intended to revolutionize calculation by mechanizing it. At his soirees, London's intellectual society watched what you see now. As Babbage cranked its handle, this machine produced a series of polynomial calculations that were repeatable and error-free. Most astonishing, it was automatic. Any of his illustrious guests might have operated the handle as well as Charles Babbage, perhaps the geologist Charles Lyell, or Charles Darwin, or Charles Dickens. Once set, the machine seemed able to proceed, to think on its own. But what was called the beautiful fragment of the machine Babbage had intended to build was all he ever finished of it. In fact, his imagination had already moved on to an even more ambitious mechanism, one that would make obsolete the abandoned machine. The Analytical Engine would be a general-purpose calculating automaton. For most of 30 years, he would revise and improve his notional design. Only a few partial sections of it were built, this one after Babbage's death by his son. The Analytical Engine was an ever-evolving machine. Each breakthrough elegantly drawn up, annotated to describe mechanical motions with a coding system that Babbage claimed was his finest invention. The Analytical Engine may be the most intricate operating mechanism ever fully realized with paper and imagination alone. In 1846, Babbage abruptly changed course. As if determined to make good on an old obligation, he worked for 2 years to complete a full set of drawings for Difference Engine number 2. It would require 8,000 parts, only a third as many as the first. He offered it to the government, but did not protest when it declined to build it, and the drawings were carefully put away. Eventually, they came from the Babbage estate to rest in the library of the Science Museum in London. More than 130 years later, in 1985, the museum's new curator of computing, Doran Swade, became convinced the institution could build Difference Engine number 2. After all, with the intact drawings, it seemed feasible and within financial reach. It took 17 years and drama to rival Babbage's so long ago. And it works, just as Babbage designed it. Every turn of the engine's driving handle is carried through gears, cams, rods, levers, and springs to release and arrest precisely aligned number wheels. A helical arrangement of steel fingers continually pulls the register towers to find and perform the carrying of tens. In its continuing sweep upward, it is mesmerizing. The intricate printing section can be programmed for 1, 2, or 3 column output, for 2 font sizes at once, for variable margins and column gaps, even word wrap where necessary. It prints hard copy on paper and simultaneously impresses the same output into a tray of plaster to produce a stereotype, a mold for casting a full-page printing plate. When a tray is full, the printer pauses the entire machine. In the spring of 2008, a clone of DE2 commissioned by Nathan Myhrvold was completed at the Science Museum and shipped to California. At the Computer History Museum, it would charm new thousands of discerning eyes. Today, the crotchety proud genius, who never managed to prove it during his lifetime, has a fair claim to honor as a pioneer in the history of intelligent machines, just as his parlor guests in 1832 suggested. His Difference Engine continues to inspire the admiration of his intellectual heirs, a celebrated and unique icon to chroniclers of computing. Charles Babbage, remember, never saw it, except in his stubborn, prescient dreams.
Okay. So, how was it? It's a big mechanical device. So, as I said, many things, many calculations that we do today, the registers, binary numbers, decimal numbers, whatever, can be implemented mechanically. The only problem is the mechanical power and the cost for fabrication. As you said, even with today's standards, it took 17 years to build it, the replication, in the museum, of course. The Lady Ada was the helper of Charles Babbage. She documented the work of the Babbage, and she was an assistant. So we know Babbage through Ada. And Ada wrote the programs to be run on Babbage's analytical machine. So what made her the first computer programmer. But since the machine was not built during the Babbage's time, Ada was unable to see the output of the programs. So there were programs written, fixed programs written, but not executed in the lifetime. The programs were like a Jacquard Loom fabric machine, weaving machine, different cards. Each card contained commands, and a series of cards will execute certain operation on the data. Then electromechanical things came up. The electromechanical things are somewhat improved version of Analytical Engine, the old mechanical Pascaline, and the arithmometer. Adding, changing digits, subtracting, shifting, multiplication, and then shifting back. So multiplication, division, addition, and subtraction can be done by this machine quite easily. If you are interested more, there are a lot of videos to teach how to use it. But basically, it is the shift of digit that makes the difference. For example, when you are multiplying 55 by 67, one idea is you add 55 67 times. If you rotate 67 times, and if you have a display up here containing 1, 2, 3, 4, if you have a revolutionary counter, if you rotate it 67 times and write 51 here, the result will show at the end 55 times 67. The result will show that, right? If you rotate 67 times. But when you want to do things a little bit faster, the decimal point shifting is important. When you shift decimal point, instead of 60 times, you rotate 6 times. Then you rotate back, shift back 7 more. So 10, 20, 30, 40, 50, 60, shift 1, 2, 3, 4, 5, 6, 7. So that makes 67. That's why long multiplications such as is somewhat easy because you start with this, rotate 6 times, then shift again, rotate 7 times, shift again, rotate 4 times, shift again, rotate 2 times, and then it is finished. It is similar to what we do in the paper and pencil calculations. When you are doing multiplication, 2 times 1, 2 times 5, 2 times 4, 8, 2 times 3, 6, and then 4 times 1, 4. So you shift, right? And then you add. So this shift is implemented mechanically, also in the Babbage's Analytical Engine. So mechanical shifting is done. The lever acts on another part of the system. That makes you a mechanical calculator, and the famous facet calculators used until 1980s because people consider those were very safe because they are doing it manually. There is no possibility of having an error. They were trustable machines. At the beginning, electronic calculators were expensive in the government offices, etc. Everywhere, those facet machines were used. When I was in high school, for example, they were in use in early 1980s. More computer-like operation was invented by Hollerith. Hollerith is a genius guy. Bende gözüküyor. Hollerith was working in IBM. Sadece sende yoktur. Tekrar bir gir çık istersen. Belki internetin gitmiştir. There was no IBM. I'm sorry. His company was the origin of the IBM. That's how we say that. In 1880s and 1889, they were making population counting and other census counting operations in the United States, successful census counting, how many people, what is the education, etc. So Hollerith, in 1880, census took 7 years to be processed. So it took 7 years to process all the data coming from different cities. Hollerith deduced that the next census would take longer than 10 years because they were asking more questions in the census, in the counting. So he invented a machine. He made a machine to make operations quicker and automated. So he invented the census counting machine, which I have the next slide. This was the Hollerith Tabulator. It could be German or German origin because the name is Hermann, but in United States. The census counting tabulator was the information was coming as cards, like punched cards, and the punch card was placed in the machine. When you push the arm down, the punch card is read, taken in, information is taken in, and counting values the correct counting values, whatever it is, I don't know, is updated. So the information storage is updated when the card is read from the machine. So this image is original photograph when the machine was in use. It was very successful. It was very, very successful. And this was the original punch card for the Hollerith tabulator. And that is actually the origin of the IBM punch card. This is IBM punch card, using a card to contain a certain piece of information. It goes back actually to Jacquard and Charles Babbage, etc. But this type of card containing information and machine readable operation, the cards that are not connected with wires. Charles Babbage's machine is like Jacquard fabric machine. The cards were connected by wires. In this one, because it was mechanical, too mechanical, in these cards are separate, and there is a card reader. And this one was card reading was done manually. Later in the IBM, card reading was automated. So previous one was 7 years, but 1890 census took just 3 months to process, even though quite a bit more data was collected than ever before. So it was very fast operation compared to the previous census in the United States. This company, Hollerith's company, tabulating machine company, became computer tabulating recording company in 1913, before World War I. And after merging with another company that produced a similar product, computer tabulating and recording company. And then in 1924, the company was renamed as International Business Machines. So these were the original logos, and this is the first logo of the IBM. Then 1956 and 1972 logos of the International Business Machines. So origin of the IBM therefore goes back to Hollerith, US census counting machine, card reader. Germans didn't stop during those times. Konrad Zuse, I have covered this a little while ago in the previous lectures, I think. He was statistical guy again with another task, and he went to military, and military said, German government said, it is not war important. Such computer is not war important, so we don't have money for that. That is what he got as an answer. Obviously, it was very incorrect. It was very wrong. Zuse, Konrad Zuse, died very in late time, in 1995. So on the internet, there are a lot of resources containing Konrad Zuse, which is very nice. And he made a complete computing machine. Program code and data were stored on punch cards, punch film, not cards, like cinema film. So, but punched, still with the holes on it. The this was an electrical machine, not mechanical. It's an electromechanical combination with relays, etc. So the relay was significant in these machines. Relay. In the same years, those relays were also used in telephone exchanges. Telephone exchanges were very complicated, with the relays and electromechanical devices selecting the target subscriber. So that kind of mechanism was a startup point for some certain inventors of this kind. ICANN. ICANN was supported by government and IBM to build computer Mark I, Harvard Mark I, and it has, again, mechanical switches, flip-flops back and forth to represent mathematical data. So there are relays, mechanical relays, again, inspired by telephone exchanges. Telephone exchange is a big computer, but it is not programmable. It is fixed programmable, so people are interacting with it to select destination, the original crossbar exchange. It's an electromechanical device, but computer inspirations came through those electromechanical devices. This Mark I weighed 35 tons with 500 miles of wiring. It's like big telephone exchange, an intelligent telephone exchange center, Harvard Mark I. Another piece of information here, Grace Hopper. This picture is in our laboratory, in the Kuwait Turk laboratory. We prepared it there. So she has the image as one of the pioneers of computer science and engineering. She was in the Navy. She was one of the first programmers and developed the first compiler. Before, all programs were written in the machine code, but she developed a language so that language can be translated into a machine code. So we can say that she is the mother of the compilers. The language she invented later turned into the computer language named as COBOL. Here is she with the President Ronald Reagan during that time. She died recently, a few years ago. President Obama gave a present to her, a medal, Freedom Medal to her, but I think she was unable to come, and somebody else came to pick up the medal. So mother of the, not father, but mother of the compilers. Okay. Also, she is the one who found the bug in the program. Actually, this is the report, original report, and the bug itself that they extracted from the machine relate to panel F. A bug is in the relay, so the relay is not working, and the program is therefore not working. Started the cosine tape, sine check, started the other test, and then there is a bug in the relay. This one is considered as a first bug found in a computer program. So by Grace Hopper. This was Mark I. That was 35 tons. So it's a big telephone exchange, electromechanical computer. Very expensive room, a lot of electricity and heat, but it was working. So it's a bigger version of, electrical version of, relay version of the Charles Babbage machine. Charles Babbage machine was completely mechanical, but these were electromechanical, meaning that there are relays, small relays, and rotating motors, positioning motors, so that you can select different target values. For binary operation, relay is sufficient, but for decimal computers, you need to be able to represent 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then next digit. 0, 5, 0 to 9, next digit. 0 to 9, next digit. Therefore, you see a lot of rotating wheels and numbers in the Charles Babbage's machine, because that was decimal, that wasn't binary. In the binary, the code may be binary, but operation, the numbers in the registers were stored as numbers. And also in mechanical calculators, they are not binary, they are decimal. So each disk contains 10 numbers rather than 2 numbers. But with these ones, when you use relays, it is on and off. Through the vacuum tubes, this was your exam question. It replaced electromechanical relays, but they were unreliable. And they were costly and unreliable, but very fast, much faster than relays. With the ENIAC 1946, 17 tubes, and every 2 days, one tube was failing, which was not significant actually. It took 15 minutes to locate and replace. So that kind of reliability was achieved in 1946. So let's come back to Turing. Died in 54, early age. English mathematician during the wartime. He was influential in the development of computer science by formalizing the concept of the algorithm and computation and the famous Turing machine and Turing test, with the role of the creation of the modern computer. Is widely considered as the father of the computer science, not the father of the computer. Father of the computer is the Charles Babbage. Father of the computer science is Alan Turing, and also the artificial intelligence. He was during the Second World War, the Germans on the right, writing the code, he made a major contribution to the development of sophisticated computing machine called Colossus by British, who was used to help crack the codes of the German Enigma machine. Enigma machine is on the right. The Enigma machine was an electromechanical machine used for encryption or decryption of secret messages. It is basically the private key symmetric cryptography today, since it is since it is based on private key and private algorithm in both sides, encryption and decryption is relatively straightforward, but decryption without private key is very difficult. So that's how Alan Turing was doing with the Colossus. Turing's work helped Allied code breakers to decrypt a vast number of messages that had been encoded using Enigma. The intelligence that is gathered from this source was very important in the winning the war, Second World War against Germans. This was the machine, Colossus, Mark I and 10 Mark II was built. First one started running in February 1944, so it is very end at the very end of the war. Mark I, the first version, contained 1,500 electronic valves. Mark II had 2,400 valves, and it was 5 times faster than the first one. So version 2 was much better than version 1. Alan Turing had personal problems due to his gender preference. He was an athlete, world-class marathon runner. He got prosecuted due to gender preferences and got treated medically, and he died in 54, several weeks before his 42nd birthday from poisoning either by suicide or by killing. Probably it was suicide. Then later in the 2009, British government made an official apology from the Alan Turing about how they treated him by conviction due to homosexuality. Let's go back to United States, and this is from the ENIAC from University of Pennsylvania. Again in the wartime, ENIAC was designed to calculate firing tables for the US Army. So what is the angle of the projectile, what should be the angle of the projectile to hit the certain target under certain conditions, etc. That kind of calculation. When ENIAC was announced in 1946, it was very famous in the world. Giant brain, so brain machine, etc. Giant brains. It was 1,000 times faster than electromechanical calculators, which was like Mark I. Harvard Mark I was electromechanical, but ENIAC was so fast, 1,000 times faster, because there were no electromechanical parts, no relays, etc. So inventors of the ENIAC promoted and spread the new technologies through a series of lectures and construction of electronic digital computers in the University of Pennsylvania in 1946. ENIAC. ENIAC was very big, 17,000 valves, 5 million hand-soldered joints, 30 tons, and took up 167 meters square. So It's very big. Input was possible from an IBM card reader, and IBM card punch was used for the output. So card input and card output. These cards could be used to produce printed output offline using an IBM accounting machine. So cards were put into card printing machine, and then human readable form can also be taken by a printing machine. Reprogramming. Task of programming of the ENIAC was very difficult because it required cable connections. After the program was figured out on the paper, the process of getting program into ENIAC was manipulating the switches and cables. It took several days. That was after a period of verification and debugging and controlling. Then using the ENIAC, von Neumann came up during the Manhattan project. Here we see Richard Feynman, Olav, and von Neumann. This guy is von Neumann in Manhattan project. So he came up an idea of using part of the internal memory to store the program inside the computer. So before von Neumann, program was something like hardwired and something predefined and must be configured. But von Neumann said, we have the memory. Why don't we use the memory to store the program? So that was the memory concept of the von Neumann, and then he got very successful, and the architecture today we use is called as von Neumann architecture, where we store program and the data in the same memory. Between ENIAC and Atanasov in the Iowa State University, there was a scandal. Atanasov and Berry, professors Atanasov and Berry from Iowa State University made a different computer. Actually, ENIAC was actually designed based on the information that is taken from the Atanasov computer. So until 1972, there was an injustice when Honeywell, the company Honeywell for Atanasov, and Sperry Rand, which was holding the Eckert and Moschly's patent after the ENIAC. So ENIAC turned into Sperry computer. Atanasov turned into Honeywell computing. They go to court, and then the injustice was rectified, and Atanasov and Berry were credited as the first inventor of the electronic digital computer, not the ENIAC. Therefore, first digital computer is not ENIAC, Atanasov, and Berry, which is then turned into Honeywell. Honeywell was still producing computing devices, computers. When I was in university, I think Koch Holding was selling Honeywell computers for some time. Then Honeywell closed the mainframe division. Today, Honeywell is a technology company and working for aviation, military, and control automation technologies. Sperry and Sperry is no more selling machines. This was Atanasoff Berry computer. It's the famous one. So it's an electronic computer, and etc. So there are mechanical parts, but data processing is electronic with the tubes. These are the tubes, small tubes you see on screen. Input and output is done by cards and cards. Later, I'm going to be quick. Later, EDSAC, as made by UK people, it was inspired by von Neumann's ideas and the first practical stored program electronic computer. So you store your program in the memory and press the start button, then it is executed. So program is not hardwired. EDSAC first program was run on 1949. Okay. Then transistor came up. With the transistor, these are the guys who invented transistors. Bardeen, Breton, and Shockley, and in the Bell laboratories. Instead of tubes, people started using transistors, and that increased the speed, reduced the current and the power consumption, miniaturized everything significantly, and also increased the reliability. Some magazine, these electronics magazines, called the device as crystal triode, because triode was tube with the same functional tube is called as triode, and crystal triode means there are no tubes but only silicon, then it's crystal triode. So what was it? What was the first thing done with transistor? A hearing aid. Hearing aid was the first thing that was done with transistor, low power and small. Then the pocket radio. Then a computer, obviously, who is paying more money? Army. Army is paying more money. Airplane computer was done because it was not heavy. So B-52 plane, this still big plane, bombarding plane. This transistorized airborne digital computer was made and completed in 1954 within the plane. This is the picture of the plane, and this is the opened gate with the same device on it on the board. In 1950s, there were Univac, IBM, and Burroughs. There were three companies who were making electronic computers. They were making a lot of money, and the computers were very expensive. Hard drive was not possible, and random access memory was not available. Random access memory was these are the memory drums. They were random access memories, so it was rotating very fast. You can read and write from the disk. So that was used as temporary memory, not hard drive. Magnetic drive but magnetic disk, but used for RAM, random access memory. Then in the 1951, again, counting Census Bureau accepted delivery of the first UNIVAC computer. Remington Rand became the first American manufacturer to manufacture a commercial computer for companies. So in the business use, not government or not only government or army. So Remington Rand was first company to deliver a computing machine for companies. First non-governmental contract was General Electric's appliance park in Kentucky. 1 year after, UNIVAC was used to predict elections. Regular polls predicted Stevenson will win. UNIVAC predicted Eisenhower will win. And at the end, Eisenhower won, and UNIVAC was right. That was very important in the history because computer was right, regular method was wrong, and the TVs and all the public opinion changed, and this new technology and new tools and computer, importance of the computer is accepted by the public after this election issue. In the popular culture in those years, 1950s, UNIVAC, name UNIVAC was used significantly for a computer. It says, our UNIVAC computer has screened applications. So in newspapers and comic books started to include the word computer and UNIVAC together. Since 1955, programming languages Fortran, COBOL, became widespread throughout the world, and the producers were very big, machines were expensive, they were getting smaller, and with the transistors they were becoming more reliable after 1955, second generation. So these are among those. IBM 1401. IBM 1401 is binary coded decimal. Not exactly binary, so binary coded decimal. There is no A to F hexadecimal letters. You have binary 0000, 0001, 000, 010, 1, no, 0, 0, 1. So this is 9, right? This is 0. After then, it goes back to 0. So no more numbers. So some digits are wasted, but that is what binary coded decimal is. Burroughs was also producing similar machines. 1956, IBM 305 was first commercial computer that used hard drive, which was 5 megabytes of hard drive. This is the hard drive is putting in the airplane for shipment, and the RAMAC actually was the acronym for Random Access Method for Accounting and Control. So it's random access. The word random access was used, and this is the control room for IBM 305. Then space race began. NASA was in the play. NASA spent billions of dollars to miniaturize the computers. First integrated circuits were manufactured. So integrated circuit idea came up. Then third generation of computers came up. This is 370 IBM. So that's the third generation computing with the magnetic tapes, etc. When we are doing programming in 1960s and 70s, people were there are no computers. You have flowchart, ruler, and flowchart symbols. So you generate flowchart. So it is so important. Even today, it is so important to analyze the problem and convert that into a computer program. So that was the IBM programmer. Data entry was done through not only by cards, but only by papers. Papers were also like Jacquard Loom. Paper tapes were also used. These paper tapes later turned into magnetic tapes. Data storage was implemented with the disk, 30 megabyte disk, 1966. It was so heavy, but that was it. More expensive hard drives in 1980, 1 gigabyte hard drive, 250 kilograms and $8,000. This was the hard drive manufacturing place of the IBM. So it had to be clean, no dust during the manufacturing. Why do we have mainframes? Mainframes evolved. Even today we use mainframes because central computation power is required sometimes. When we have client-server computations, today, since network is sufficient enough, it might be wise to use centralized, very high-power computational device because data is stored there. So banks, research companies and research centers, government and big hospitals and accounting things require mainframe computing. So personal computing is only for some certain things, but if the data is big and if there is intelligence, prediction is required, big intelligence is required, artificial intelligence is required, significant power is required, still we need very powerful machines. Much more powerful machines is required in future with the deep learning algorithms becoming popular. We need more powerful machines. And one example is IBM mainframe series. These are modern versions of the old mainframes, IBM Z15 and IBM Telium. These are the new ones. So these are the new looking mainframes. So when you go to the banks, big data centers, when you talk about mainframes, these are the mainframes. They are basically cabinets. And the power is what happened? What happened? Next slide. Okay. The new these Telio mainframes have 256 cores on 32 CPUs, and they work at 5 GHz. So it combines multiple cores into single chip and has many of those chips in the same enclosure. We have a short 1-minute video on this.
The Talon processor's AI capabilities have been specifically designed for low latency real-time AI so that it can be embedded in transaction workloads. To you as a consumer, that might, for example, mean that a model to predict credit card fraud can be applied in a way that the fraud gets detected in time before the transaction even completes. The chip contains 8 processor cores running at more than 5 GHz. The processor cores are what's executing the actual program. And then each processor core is connected to a 32 MB private level 2 cache, which contains the data so that the programs can get to the data they need to operate on very quickly. All the caches are connected with a ring. Think of this as a data highway along which we can send the data between the different caches when different programs need to communicate with each other. And that way we build up a 256 MB cache for the entire chip, holding a lot of data for all these programs executing on these cores. The AI accelerator has its own entry and exit to the data highway so that it can get to the data in the caches, perform the AI operation that's necessary, and then put the result back onto that entry to the highway, put it back into the cache so that when the program continues using the AI result, that result is right there in the cache and readily accessible by the core. Up till now, there are chips that are dedicated to AI, and there are server processors that run enterprise workloads like databases and transactions. The Talon chip brings those capabilities together to enable our clients to embed AI directly into their transaction workload.
Obviously, a mainframe has multiples of these chips and vast amount of storage. The price of Z15 mainframe, it starts from $200,000 and goes up depending on the configuration. Depending on the configuration, it goes up. So if you have any questions, let me know. Do you have any questions? Okay, let me stop recording. Maybe you have questions without recording.